in the first lecture, I tried to motivate you how we can probe cosmology with gravitational waves. And as I tried to explain, there are two ways, or two particular, there are two ways that we can go about things. So the first, which is the one we discussed on Tuesday, was to study individual sources of gravitational waves on cosmological distances. And with these, we can learn about the late time universe. And as we saw, maybe I can just summarize what we discussed the other day. So what we learned in the first lecture was that when we observed the gravitational waves from a binary system, such as a binary neutron star or a binary black hole or neutron star black hole binary, from the observation, from the data, we can extract the luminosity distance to the source. So that comes as, I mean, we saw that the waveform goes as 1 over the luminosity distance, and so we in principle have a direct measurement of the luminosity distance. And then we saw that in order to extract cosmological parameters from that, we need to have a measurement of or a way of estimating the redshift to the source. And I tried to give you a certain number of ways in which one could think of extracting the redshift. The first one is if you have, is the most direct, if you have an electromagnetic counterpart to your event, and you're lucky enough to observe it, then that will give you directly the redshift of the source. It's possible that your event is sufficiently well localized in the sky that and not too far, so that there are galaxy catalogs which you can use to extract the redshift. And some more tentative, but hopefully I think interesting methods which can be applied also to binary black holes, which won't have most likely electromagnetic counterparts, is to try and learn something about the redshift through the properties of the populations of those objects. So I tried to motivate the fact that I think that in the future, with the Einstein telescope in particular, doing cosmology will really go hand in hand with doing astrophysics. So my feeling optimistic, I think that in the near future, with these different methods, with these observations, and with the future detectors, so Einstein telescope, LISA, and also with hopefully with the advanced LIGO, we will have important information and important measurements of cosmological parameters, resolving the Hubble tension, or possibly not, if there's new physics involved, and new physics is something which we'll be discussing today. Now, there are a number of, when one wants to go sort of down this method to extract cosmological parameters with future detectors, I also tried to explain to you that there are a number of new effects which we'll have to consider when we're looking at very large redshifts. So in particular, the effect of overlapping sources. There could be higher order modes, there could be processing spins, and there are a number of open questions, which I think will be very interesting in the future. So that's more or less what we discussed on Tuesday. Today, I want to discuss the other aspect of cosmology with gravitational waves, namely how we can study phenomena in the very, very early universe at any time after the Planck time by studying the stochastic background of gravitational waves of cosmological origin. And if I have time at the end, I also want to go back to this left-hand side and talk about possible measurements or constraints on theories of modified gravity using binary systems. But I'll start with the stochastic background. And let me just say straight away that this second lecture, in a sense, is a lot more speculative, because I'll be discussing either physics beyond the general relativity when I discuss modified gravity, or on the right-hand side, we'll be discussing sources of a stochastic background of gravitational waves, which are hypothetical in the sense that they're based on physics beyond the standard model of particle physics. So it's a much less certain situation. Okay, so as I said, I'm going to want to start on the right-hand side here, and if there's time, go back to the left-hand side. So probing the very early universe with gravitational waves, as we saw last time, I argued that this can be done by looking at the stochastic gravitational wave background. So we're no longer talking about individual sources, which you can see, but rather the superposition of gravitational waves arriving from random times and random directions. And the idea is that they overlap so much that you can't see them individually. Now, in fact, there are two components, at least to this stochastic gravitational wave background. One is astrophysical, and the other one, which is the one which interests us here, is cosmological. So the astrophysical one is due to all those sources which we've already, in part, already talked about. So there's going to be a large number of black hole mergers and other astrophysical events which can source gravitational waves, but too weak for us to be able to resolve individually. And these will contribute to the astrophysical background, which is generally larger than the cosmological background, which, as I said, is the one that we want to focus on. So it comes from events very early in the history of the universe. And here I'm going to focus on a number of different events. I'm going to focus on the effect or a possible stochastic background generated by phase transitions in the early universe. So phase transitions can go through the expansion of bubbles and colliding bubbles, and these bubbles can create a background of gravitational waves. I'm going to talk about topological defects such as cosmic strings, which are also the result of phase transitions. Then there are also processes during inflation which can generate a stochastic gravitational wave background, though it's in the standard models it's going to be very difficult to see. And then there are many other possible sources of the stochastic background of gravitational waves. Now these two backgrounds, differ in their properties because of the symmetries of the Friedmann-Robertson-Walker metric. We expect the stochastic gravitational wave background to be nearly homogeneous and isotropic. And because there's no sign of parity violation in the universe, we expect it to be unpolarized. And because we're looking at the overlapping of many, many sources, we expect it to be Gaussian. On the other hand, the astrophysical stochastic gravitational wave background is likely to be anisotropic, but strongly directed or strongly concentrated in, for example, in the direction of the Virgo cluster, where one expects there to be lots of astrophysical activity generating the astrophysical background. So our focus is the cosmological background. And as I explained on Tuesday, it's the analog of the cosmic microwave background of photons produced at decoupling, but with the crucial difference, and I explained why, it's because of the weakness of gravitational interactions. So the crucial difference being that gravitons are decoupled below the Planck scale. So the stochastic gravitational wave background gives us direct access to the earliest stages in the evolution of the universe, which we can't access directly through electromagnetic radiation. But because we're talking about the earliest stages in the evolution of the universe, we're talking about predictions based on physics beyond the standard model of particle physics, and possibly also beyond general relativity. And the corollary of that is that by default, any predictions that we make will be uncertain because they're based on unknown physics, untested physics at least. And the second corollary, though, is very exciting because if we do see a stochastic gravitational wave background of cosmological origin, then it has a huge discovery potential because it would be telling us about this physics, which is so far is untested in accelerators, for example. So that's the really great interest in the or potential of the stochastic gravitational wave background. Okay, so what stages of the universe are we talking about? So here again is the picture of the cartoon of the expansion of the universe from the Big Bang through inflation. Then at these kind of energy scales of 100 odd GeV, there's the physics, particle physics, which is being tested in accelerators. The universe is expanding. There's at some stage, there's Big Bang nucleosynthesis. Equality, the cosmic microwave background is produced, and then there's structure formation and dark energy, which we mentioned last time, the accelerated expansion of the universe, and various things where we are today, including this not very nice one. And so cosmology, the realm of tested cosmology is essentially starts sometime before Big Bang nucleosynthesis. So times of the order of something greater than 10 to the minus 3 seconds, or temperatures less than of order 100 MeV. Tested particle physics is somewhere beyond this purple line here, so at energy scales less than of order 1 TeV. And so we don't really know what physics is going on below here. And so there could be new physics. And as I've tried to say, the stochastic background of gravitational waves is cosmological origin is a fantastic way of probing this new physics, but it gives uncertain predictions because we're not sure about that physics. Okay, so in this second part, I want to go into a bit more detail in on the stochastic gravitational wave background. So I split it into at least five sections. So the first one is quite general. So I'll be talking very generally about the properties or some properties of the source, or trying to really stress the difference between the three sources I want to discuss, and also explain why we're talking about the stochastic gravitational wave background. Then I want to try and characterize the properties of that background, typical frequency and amplitude, for example. Then I'll try and summarize briefly the experimental bounds which exist today on the stochastic gravitational wave background at different frequencies. Then in part 4, we'll introduce the source and do a simple calculation of the spectrum of the stochastic gravitational wave background. And then I'll talk in a bit more detail about these three different sources. So in particular, bubble collisions from the electroweak phase transition, cosmic strings, and inflation. Now I should say that there's a really beautiful review on the stochastic gravitational wave background written by one of the organizers of this workshop, so Chiara Caprini and Danièle Figueroa. And I've based a lot of these lectures on that review, so you can find the reference here, and also by a set of lectures by Chiara herself. So if you want more details on this subject, I really advise that you go and look at this review. Okay, so let me start with some generalities and maybe some reminders for some of you, I'm sure. Because I don't want to stick with cartoons, I want to have something a bit more concrete. So let me start with generalities first about the sources that I want to talk about. And so the different sources that we'll see, they have very different properties and they're going to give very different stochastic gravitational wave backgrounds. And to discuss these, the differences between the sources, I want to go back to basics for a second, because I think it'll be very useful later on. So on Tuesday, we already wrote down the unperturbed Friedmann-Lemaitre-Robertson-Walker metric. So either in terms of time, t, with scale factor a of t, or in terms of conformal time, eta, multiplied by the Flat-Minkowski metric. Now, if the scale factor, and this is a simpler case we'll consider, if it goes as a power law, so t to some power p, then I think you'll know that p is equal to half in the radiation era. P is equal to 2/3 in the matter era. And to have accelerated expansion, so inflation, P has to be bigger than 1. Now, the physical quantity of interest to us will be the Hubble radius. So it's 1 over the Hubble parameter. So A over A dot. And the corresponding co-moving Hubble radius, which is the same quantity divided by A. So if we divide by A, the A's cancel, and so it's 1 over A dot. Now, it will also be useful to work in some of our equations in terms of conformal time. So the definition of conformal time comes from here. So it's the integral of dt over A. And it's a very simple exercise to show that if A goes as t to the power p, then A goes as eta to the power q, conformal time eta to some power q. Q and p are linked in this way. So q is equal to 1 in the radiation era. Q is equal to 2 in the matter era, and Q is negative because P is bigger than 1 during inflation. And then the co-moving Hubble radius, which is here, I can rewrite in terms of derivatives. So prime means a derivative with respect to conformal time. So A dot becomes A primed over A, which is 1 over the conformal Hubble factor, curly H. And so if you take the fact that A goes as eta to the power q and you substitute it in here, you find that 1 over h goes as a to the power 1 over q. And so if I take the log of both sides, log of h inverse goes as 1 over q log a. So now let's plot the log of the co-moving Hubble radius as a function of log a. So here it is. So here I've just taken the same expression we had before, log of h inverse goes as 1 over q log a, and I'm going to plot it as a function of log a. So in the radiation era, we saw that q was a 1, sorry, in the matter era it's 2. So in the radiation era, the gradient here is 1. In the matter era, the gradient is a 1/2. And during inflation, we said q is negative. And if it's de Sitter inflation, in fact, you can show that the gradient here is also -1. So there's the period of inflation in the early universe. Inflation ends, and it's followed by a radiation era and then a matter era. And on this plot, I've drawn 2 fixed co-moving scales, λ2, which is bigger than λ1. So as I think you've all seen in lectures on inflation. So, well, before we get there. So if you see the mode λ2, it starts being subhorizon during inflation. It exits the horizon and becomes superhorizon for a period of time before re-entering the horizon, in this case during the matter era, when it becomes subhorizon again. So what are the sources of the stochastic gravitational wave I want to talk about? Well, the first one is this inflationary period. So as I think you'll probably have seen in other lectures, during the inflationary period, vacuum quantum fluctuations are generated on all co-moving scales. They oscillate when they're inside the horizon. Their amplitude is frozen outside the horizon, and then they re-enter the universe during the radiation or the matter era, setting the initial conditions for the hot Big Bang model. Now, generally, I mean, of course, these perturbations can be either scalars or tensors. If they're tensors, they're gravitational waves. And it's precisely these gravitational waves from inflation which can lead to a stochastic gravitational wave background. So that's one source of the stochastic gravitational wave background. Another source of that I want to look at is the electroweak phase transition, or something which occurs at something which occurs on a short duration of time, so short compared to the Hubble parameter, the Hubble distance, okay, or the horizon. So delta eta much smaller than H inverse. It occurs for a short period of time during the radiation era. And the electroweak phase transition could be taken as an example of that, at an energy scale of order 100 GeV. And the third source, which I want to focus on, is not something which is going to be short duration like this one, which switches on and then switches off over a short period of time. But it's going to be a source which is produced at one period of time during the expansion of the universe, at hypothetically at the phase transition associated with grand unified theories, so 10 to the 16 GeV. So it's going to be a source in the form of cosmic strings, and the difference between cosmic strings, or this particular source, and the electroweak phase transition is that whereas this one is thought to be short duration, cosmic strings exist throughout the entire history of the universe. So it's a source which will be present the whole time, even until today, always generating gravitational wave perturbations, and hence always generating, possibly generating a stochastic gravitational wave background. So hopefully you see these three sources have very different properties. One is due to inflation, so the amplification of quantum fluctuations. The others are using causal physics in the radiation era. One is a short-lived source, and the other one is a long-lived source that exists until today. And they'll give quite different gravitational wave spectra. Okay, then I think the next question one can ask is, why am I talking at all about a stochastic gravitational wave background? In what sense? Why is it stochastic? So let me try and explain that. So here's my figure again. Okay, and I'm going to consider a source which is operating at some time t. So this is in the standard phase of expansion of the universe. So I'm not talking about inflation. So some time t star in the radiation era, for example. So let's assume the source operates at this time t star in the radiation era, and try and answer the question, why does it generate a stochastic gravitational wave background? Well, firstly, from causality, we know that the signal which is produced by this source can be correlated on length scales or time scales which are at most as large as the causal horizon at that time. So if we call L star the characteristic length scale of the source, then that L star has to be less than or equal to the horizon, causal horizon at time t star. Okay. Now you can take that length scale at time t star and redshift it to today to find out what length scale it corresponds to today. So this is L star 0. And you can then compare it to the Hubble radius today. So you want to take the ratio of L star 0, so the size of this length scale L star as measured today, divided by h minus 1, h inverse today. Now to do that, you have to use the Friedmann equations. And I've not put the details here, I've just put the order of magnitude. By the way, I've saturated this bound. So I've assumed equality. I've also made a number of approximations neglecting changes in effective number of relativistic degrees of freedom. And I've assumed that there's no matter era, that we're in the radiation era all the way till today. But the order of magnitude is approximately this. The size of this length scale redshifted to today divided by the Hubble, the causal horizon today, is of order 10 to the minus 11 for a temperature T star at which the source operates of order G. So T star to the fourth of the order of a GeV. So if this source operates at any reasonable temperature in the radiation era, then this correlation length is tiny compared to the size, the present size of the universe. Okay, and then you can, so clearly we're talking about lots of little patches inside the huge Hubble patch. And you can even ask, what's the angular size of that patch on the sky today? So the angular size of that patch on the sky today is simply L star divided by the angular diameter distance, whose expression is given here. And so you can calculate that quantity as a function of Z. So here again, you would have to saturate the equality. So you see theta star is a function of the redshift at which the source operates. If you replace L star here by H inverse, which is also a function of Z, you can calculate theta star as a function of Z star. And the number of uncorrelated regions today from which we receive independent gravitational wave signals is of the order of this angle to the -2. And again, you can calculate it. So for example, at electroweak scale, so temperatures of order 100 GeV, you find that theta is of order 10 to the -12 degrees. So in other words, the gravitational signal, wave signal, as received today on Earth, due to a causal process operating at the electroweak epoch, is composed of a superposition of about 10 to the 24 independent signals emitted by at least 10 to the 24 uncorrelated regions. You can do the same calculation at equality and you get an angular size of about 0.9 degrees. So the conclusion is that a gravitational wave signal from the early universe can't possibly be resolved beyond its stochastic nature. So we can only talk about or measure the statistical properties of the signal, and we need to treat the gravitational wave perturbation as a random variable. Now, of course, we only have one universe, but if we observe large enough regions of the universe, or a given region for a long enough time, we in principle have an access to many realizations of the system. So it's what we can do in practice is replace ensemble average with volume or time averages. So that's the way we're going to approach this problem. Okay, so we have a stochastic gravitational wave background. So now I want to characterize it. So we already saw some of this last time. So if we perturb the Friedmann-Robertson-Walker-Lemaitre metric, ignoring vectors and scalars, then we're talking about the gravitational wave perturbation Hij, which should be transverse and traceless. And from the Einstein equations, it satisfies a damped sort of wave equation with a damping from the Hubble expansion. And it's sourced, as we already saw, by the transverse and traceless component of the perturbed stress energy tensor, because the background stress energy tensor is what's sourcing the background expansion A of t. So this would be a perfect fluid source. So this is the equation which we want to study and we want to solve. So let's rewrite it in Fourier space and in terms of its polarization components, plus and cross. So here we are, I've split it. So here's the Fourier transform. And with the polarization vectors ER, so R is plus or cross, which I'm summing over. And the polarization vectors are given here in a standard right-hand basis. So I'm doing the same thing for the Fourier transform of the gravitational wave Hij and the Fourier transform of the TT, sorry, I haven't put TT, I've probably dropped the indices TT now. So the transverse and traceless part of the perturbed stress energy tensor, so the anisotropic stress. So if you substitute the Fourier transform into our perturbed equation and you convert into conformal time, then the equation reduces to this one. So I remind you that eta is a derivative with respect to conformal time. The 3 becomes a usual factor of 2. And the source here is, there's an extra factor of a squared from the transformation from physical time to conformal time. And it's the source and the source pi, okay, TT, of course, which I've dropped. Now, one thing which I may end up doing later is to replace the factor of a squared here using the Friedmann equation. It turns out to be quite useful sometimes. I just remind you that if you take the Friedmann equation and you multiply it by a squared, you get an equation for the conformal Hubble factor, so h squared, which is given by rho bar. So this factor of a squared is sometimes replaced by h squared over rho bar. So it's something I end up doing a bit later on. Okay, so this is our equation for the polarization components in an expanding universe, in a Friedmann-Robertson-Walker universe. And we now want to discuss its statistical properties. So as I already said, in general, we expect the stochastic gravitational wave background to be homogeneous and isotropic. And as I said, that's inherited from the FRW metric. So that means that the correlate of Hij at a point x and time eta1, and HLM at a point y and conformal time eta2 should be proportional to the modulus of the distance between the 2 points. So that's the condition inherited from homogeneity and isotropy. We expect it, as I said, to be unpolarized because we don't know of any significant source of parity violation in the universe. So we expect that the correlate of H plus with H cross to vanish. And we expect it to be Gaussian because it's formed from the emission, as we've seen, of many uncorrelated regions. And since it's Gaussian, it should be characterized by its 2-point functions. All two endpoint functions can be written in terms of the 2-point function. So let's try and rewrite these conditions in terms of the Fourier amplitudes, HR, which we already defined, they're down here. So in Fourier space rather than in position spaces here. So the Fourier components, the 2-point function of the Fourier components is given here. So there's H of R, so I remind you is either plus or cross at a wave vector K and conformal time eta, and its complex conjugate at wave vector Q. And so it inherits on the right-hand side a delta function in K minus Q because of the homogeneity and isotropy. A delta function in the polarization indices because we're assuming the background is unpolarized. And I've put various factors of K here in front and 2 pi so as to simplify expressions later on. And the amplitude here is HC squared, which is going to be a very important quantity, which depends on the modulus of K and on conformal time. So in terms of this HC, we can go back to the correlator in real space. So you can calculate this 2-point function in real space with the same indices Ij. And it turns out, because of the factors of pi which have been correctly chosen and the factors of K which have been correctly chosen, that this turns out to be an integral dk over K, so log K, of Hc squared. So you can think of Hc as the characteristic gravitational wave amplitude per logarithmic wave number interval and per polarization state at time eta. Now, it turns out that the gravitational wave energy density will be expressed in terms of this Hc, which we'll see in a minute. But let's first write down the gravitational wave energy density. So this comes from the stress energy tensor for gravitational waves, which can be written, so it's basically H dot squared, which can be written in terms of H prime, derivative with respect to conformal time with a relevant factor of A. And I can rewrite it also as an integral over d log K of the crucial quantity, so the spectrum of gravitational wave energy density per logarithmic wave number. So d omega GW by d log K, which is a quantity we're going to be trying to calculate for our different observables, our different sources. Another related quantity is the gravitational wave energy density parameter. So it's basically the energy in gravitational waves, so d omega d log K, at today's physical frequency, so you need to take into account redshifting, and normalized by the critical energy density of the universe. Okay, right, and let me just say, in fact, that often one doesn't just consider this omega GW, but in fact, h squared, little h squared times omega GW. So I remind you that little h, sorry, I didn't write it here. The Hubble constant is, given its value as we saw last time, is somewhat uncertain. Sometimes it's written as 100 times a little quantity, little h, in the right relevant units. And so this uncertainty on the Hubble constant is often translated into multiplying this quantity by this, sorry, the famous little h. Sorry, I didn't write it down. It makes more sense when it's written down. Okay, so now I want to do an exercise, just so that we see if we try and see if we understand these equations. I want to try and calculate this quantity for free gravitational waves. So I want to calculate the spectrum of gravitational wave energy density per logarithmic wave number for free waves. So here's our fundamental equation. And since I want to talk about free waves, I want to set the source here to 0. Okay, so there's no source. I'm assuming they've been sourced. And now I want to see how they evolve. So we want to solve the homogeneous equation with the 0 on the right-hand side, which is what we already did, in fact, last time, but let's see that again. So the trick is to change equation from little h to capital H. I think I called it Q the other day. So capital H is A times little h. And so our equation, our homogeneous equation, becomes like an oscillator equation with, in principle, a time-dependent mass term. And in fact, for power law scale factors, which we saw at the beginning, then A which goes as eta to the power q, then you can show that this term is essentially the Hubble parameter squared. So if this term is the Hubble parameter squared, we can look at two regimes for this equation. So sub-Hubble modes in which the first term dominates. So the first term dominates, so we have plane waves, solutions for capital H, which means that little h is capital H over A. So it's exactly as we saw last time. This solution describes plane waves with a redshifting amplitude. And we can also solve it on super Hubble scales when this term is going to dominate. And here the obvious solution, if you think about it without the K, is that capital H is A. Okay, and so little h is a constant, which is this first term. There's also a decaying solution, which is given by the second term. Okay, so there's a decaying term, but otherwise the modes are frozen outside the horizon, okay, which is basically saying here on the diagram, super Hubble modes, they're frozen outside the horizon and they oscillate inside, basically as I drew at the beginning. Okay, so here, now I want to focus on the sub-Hubble modes. And as I said, the aim is to try and calculate this quantity, the GW by d log k, focusing on sub-Hubble modes. And to help us in the calculation, I've started by collecting some of the relevant expressions. So the first one was the expression for the polarization HR of the gravitational wave, which we just had before here, right? So this expression. Another useful thing is the fact that the integral of e to the I k minus q times e to d eta is proportional to a delta function, which will be useful in a minute. And thirdly, I've just written again our definition of the correlator HR, equal time correlator HR, HP, in terms of HC. So let's calculate this correlator for our free sub-Hubble modes. Because the aim is to estimate HC, and then from there we can get the gravitational wave energy density. So let's start with the left-hand side, okay, in which I want to substitute the expression for HR here and HP star, okay. So as I think you can do it in your head, there's going to be a factor of A squared, okay, from the product. So here's the factor of A squared. And then there are going to be 4 terms. There's going to be a term in A star, a term in A B star, a term in BA star, and a term in B star. Now, we need to take the average, or time average in this case, and using this expression, you can show, or you can see, I think quite easily, that all the terms which are going to have a plus sign will give a delta of k plus q, but k and q being the modulus of the vector, k plus q is not going to vanish. So in fact, the only terms which left, so the cross terms between A and B vanish, and you're only left with the terms in A and the terms in BB. So from here, you can read off at least the time dependence of HC, okay, because you can compare it to the, so this is meant to equal the right-hand side. So the time dependence of HC is therefore given by, well, HC squared goes as 1 over A squared, so HC goes as 1 over A. Okay, that's the first point. And actually, whilst we're about it, well, no, maybe let's do that in a minute. So for the energy density of gravitational waves, so I've copied again the same expression as before. So here's the energy density. It depends on the time derivative squared of Hij. So we need to do the same calculation for H primed. Right, so if we do the same calculation for H prime, so firstly we have to calculate the derivative of H with respect to conformal time. And you can see that there'll be, each term will give rise to 2 terms. So one comes from the derivative of the exponential, which was proportional to k over A. And the second one comes from the derivative of the scale factor here in the denominator, which gives a term in minus A primed over A. So basically, you can see that the derivative H primed of this term will give 2 terms, one being proportional to A, and another one being proportional to A primed over A, which is essentially H. But since we're interested in sub-Hubble modes, sub-Hubble modes, K is much larger than H. So in fact, you can neglect that second term. And so when you calculate the correlate of H primed, you're in fact left with K times or K squared times the first correlator, if you want. So in other words, this correlator is proportional to some amplitude X, and you can show quite simply that for sub-Hubble modes, X is K squared times HC squared. And HC itself goes as 1 over A. So if we put that together, we see that omega gravitational waves has a factor of 1 over A squared in the denominator. And in the numerator, there's this factor of H prime squared, which itself goes as 1 over A squared. Okay. So the conclusion, putting that together, is that omega gravitational waves goes as 1 over A to the 4th. And so as you'd expect, the gravitational wave energy density is diluted like radiation, at least to freely propagating sub-Hubble modes. And that's something that we mustn't forget, because it's going to contribute to the right-hand side of the Friedmann equation, and it's going to be important for constraints later on the stochastic gravitational wave background. And finally, I've just written down a formula which is often very useful in this game, which follows directly, in fact, from here, which is the spectrum, d omega GW by d log k. And you can read it off by, in fact, from here. It's given by k squared hc squared over this quantity. Okay, so that was the spectrum for free waves, sub-Hubble modes in particular. Now I want to ask now I want to actually try and put the source back in. Okay, so add the source and try and discuss some of the characteristic, or at least the characteristic properties of the spectrum that we expect. So the first question we can ask is, what's going to be the characteristic frequency of our spectrum, at least for causal sources, by which I mean not inflation. So the characteristic frequency, so essentially where one would expect some kind of peak in the spectrum or some some shape or particular feature in this feature, let's say in the spectrum, will depend on the production mechanism. That's clear. So that's model dependent. And there'll also be a kinematical contribution just simply from the redshifting from the redshifting from the period of production of my gravitational waves by the source. So let me try and explain that a bit better. So if we look at gravitational waves produced with a frequency f star by a source which is operating at time t star, then we can estimate their characteristic frequency today simply by redshifting the frequency. Okay, so the characteristic frequency today would be the frequency at which they're formed times the factor of the ratio of the scale factor at the time of formation over the scale factor today. And using standard cosmology, assuming a radiation era, you can express the scale factor at formation, so time t star, in terms of the temperature of the universe at time t star. And you see that the characteristic frequency is of order 2 times 10 to the minus 5 times the frequency in units of h times the temperature measured in units of, well, for a characteristic temperature of 1 TeV. Now, what else can we say? So the frequency at formation, or the gravitational waves produced with frequency f star at time t star, should typically be of the characteristic size, or 1 over the characteristic size of the source at time L star. We already saw L star. And we already argued that by causality, L star, or L star itself had to be smaller than H inverse. So 1 over L star had to be larger than H at the time T star. So if we put that back in here, we can replace F star by 1 over L star. And if we saturate, well, let's not saturate the equality. Let me write this. Sorry, I've written it here. I should have written it before. Let me write L times H, putting the L on the other side, as epsilon, where epsilon has to be less than 1. And so I can write this characteristic frequency in terms of epsilon, and in terms, again, in terms of the time at the source. And so I get that the characteristic frequency is of order 10 to the minus 7 times t, now I've measured it in units of GV, divided by this epsilon, which itself by causality has to be less than 1. Right, so let's try and plot that and think a little bit more about it. So the characteristic frequency for a source operating at time t star, measured in units of GV, is given by this expression. So we can make an example, for example. So let's take the example of the electroweak scale, t star of order 1 TeV. Then you can find the characteristic frequency is of order of the millihertz, which is in the Lisa band. So here I've drawn this, I've plotted log of the characteristic frequency as a function of log t. So the black line is in fact this equation. So that's log t on the x-axis, the characteristic frequency on the y-axis. And I've drawn the sensitivity bands of the different detectors, which we discussed already on Tuesday. So there's LIGO, of the order of the hertz, Lisa of the order of millihertz, pulsar timing array, which I'll mention, and I think you'll have heard about in other lectures, and also the CMB, which we can use to put constraints on gravitational waves, and as a function of the characteristic temperature. So the great science potential of the Lisa satellite for the stochastic gravitational wave background is that it is particularly sensitive to events occurring at the electroweak phase transition, or in energy scales of the order of the TeV. In fact, the QCD phase transition turns out to be in the frequency band of pulsar timing. So that's also a very interesting energy scale to look at. inflation happens, of course, at much higher energy scales, which doesn't correspond to any particular detector, so you might be a bit concerned about that. But so you can ask yourself the question, can gravitational waves probe this very, very high energy scale of the order of 10 to the 16 GeV or not? So what goes on at the high energy scale? So there could be inflation, for which the characteristic, so inflation at 10 to the 16 GeV, the characteristic energy scale, frequency, sorry, is about 2 gigahertz. And you could even go further up to the Planck scale. Maybe you could want to probe quantum gravity, for example, at some energy scale of the order of 10 to the 18 GeV, which corresponds to a characteristic frequency of about 100 gigahertz. So as this plot would seem to suggest, that's completely outside the scope of ground-based interferometers in LISA and of all these detectors. Now that's actually a pessimistic conclusion, because in fact the previous arguments, if you think about them, they actually show that the spectrum of gravitational waves, just through causality, has to decay at frequencies above the characteristic frequency. But it doesn't mean that the spectrum, it doesn't say anything about the spectrum at lower frequencies than this characteristic frequency. For example, if the spectrum was flat below this characteristic frequency and with a high enough amplitude, then it could be seen at lower frequencies. And so it could be seen, for example, by ground-based interferometers or by LISA. And in fact, our examples will show, especially, for example, in the case of cosmic strings, that the spectrum is in fact nearly flat over a very large range of frequencies. Okay. So the next question, what are the existing experimental bounds on the stochastic gravitational wave background? So here I've multiplied by this factor of little h squared from the uncertainty to have something which is independent of the precise value of the Hubble constant. So h squared omega gravitational waves. So the y-axis is h squared over omega gravitational waves as a function of frequency. So this is an exciting period because there are new constraints coming in. So already from the LIGO-Virgo collaboration, there was a recent paper, here's the reference, very recent, which put an upper bound, a new upper bound on omega gravitational waves in the frequency band, of course, of LIGO, which is less than, well, it depends on the assumptions for the frequency dependence, but it's basically less than something of order 6 times 10 to the minus 9. So it's approximately the order of 10 to the minus 9 here. Then at lower frequencies, so in the range of pulsar timing, so the frequencies of the order of the inverse year, there's been a recent claim by the nanograph collaboration, which I'll mention in a second. So a recent bound that you can find about in this paper. And then using CMB physics. So CMB physics also bounds the stochastic gravitational wave background, because if you have too many gravitational waves, they'll generate by the Sachs-Wolf effect some too many fluctuations in the microwave background temperature. So those are constrained by Planck. And similarly, they'll generate B-mode polarizations, which have been constrained by Lightbird. So there are also constraints at low frequency. I'll talk about these two lines in a minute. So the cosmic microwave background constraint is, I won't say much more than what I've already said. So it's constrained by Planck because basically of the Sachs-Wolf effect, the existence of a gravitational wave background, so of non-zero Hij, deforms space-time. So when photons, the geodesics of photons are modified, and so these induce temperature fluctuations, which are constrained by Planck. And the polarization of the CMB is also sourced by tensor perturbations, and has been constrained, or is being constrained by a number of different experiments. So those are the CMB constraints down here. The pulsar timing constraints at frequencies of the order of the inverse year, I won't say much about. I'm not an expert on them at all, and I think that hopefully you've heard about them from other people. But the basic idea is that the pulsars are basically rapidly rotating magnetized neutron stars, and they emit beams of electromagnetic radiation. And so you have regular trains. It's like a bit like a lighthouse or the Eiffel Tower at night. You have a regular train of pulsed radiation reaching the Earth each time the beam crosses your line of sight. And the arrival times are predicted extremely accurately. So they act a bit like stable clocks. And of course, those arrival times will vary if you have a metric perturbation. And it's using the variation of those arrival times that you can constrain the stochastic background of gravitational waves. So the recent result by the Nanograv collaboration, in fact, here I haven't taken a plot from their paper, but I've taken a plot from this other paper, whoops, another paper down here, which is to do with cosmic strings, which is why I preferred this plot. So what's on the different axes here? So what they do is they take this HC, characteristic amplitude, which we already discussed. They write it as A times some power F to the alpha, from which, using expressions we've already seen, omega gravitational waves is h squared times F. And so you can write, just calculate the factors of alpha. You can write it as a power F to the 5 minus gamma, where gamma is 3 minus 2 alpha. So this plot has on the x-axis the amplitude, on the y-axis, sorry, the log of the amplitude A. And on the x-axis has a spectral index gamma, which is 3 minus 2 alpha. And the contours are the 1 sigma contour coming from Nanograv. So that's an important new constraint, which will be important also for cosmic strings, as is. In fact, we'll see this later on. Okay, then there's the final band, which are these two dotted lines, so CMB and BBN. And simply speaking, where do they come from? They come from the fact that gravitational waves contribute to the energy density in the universe, as we've already seen. If they're free, their energy density scales as 1/8⁴ as radiation. So they enter as a source on the right-hand side of the Friedmann equation. And so they'll modify, if their energy density is too high, they're going to modify the evolution of the universe. So that puts constraints on them, because if you modify too much the evolution of the universe, then you're going to modify, for example, Big Bang nucleosynthesis. If you have a too high Hubble factor, then that feeds into a larger freeze-out temperature, and it leads into all sorts of problems and overproduction of helium-4. And so there are bounds on the integrated gravitational wave energy density generated before BBN, and that's what this orange line is here. And similarly, there's a bound on the integrated energy density generated before photon decoupling, because otherwise there would be a significant effect on the monopole and anisotropy spectrum of the CMB. So that's the dotted line. So when making predictions from your favorite model, you have to make sure that you satisfy these different bounds. Okay, I suggest we take a 5-minute pause, if that's okay, before we talk about the source. Is that okay?
Yes, perfect. I think we can also take advantage of this to ask if there are questions in the audience. Yeah, maybe it's a good time if some clarification is needed, or if there is any question or any comment. Yes, Luis Longo, go on.
Hello, can you hear me?
Yes, we can.
Okay, I was wondering if you briefly mentioned about the constraints on the amplitude of the stochastic gravitational wave background due to the Sachs-Wolf effect. I wonder if this put constraints in all different frequency bands, because we have also the background from unresolved sources, astrophysical sources. Do this constraint also concern the astrophysical sources or not?
Sorry, let me think about that question. So your question is, sorry, let me go back. Let me try and find it, sorry. Your question is, so does this, sorry, so here here the H here is the perturbation of the metric. Is your question saying that astrophysical sources will also produce, I guess, gravitational waves, right? Yes. And would they also impact the CMB? Is that your question?
Yes. And if so, what is the current constraints with that? It gives constraining the astrophysical sources gravitational wave background, because I guess that the frequency content is completely different from the cosmological one.
Right, so I'd have to think about the answer to that, but of course there's a huge amount of work in the CMB is precisely subtracting the foregrounds, right? So so the answer is I need to think about it, but I suspect that I suspect that it only applies to or at least the way I want to apply it is only to the cosmological stochastic background. Okay.
Okay, thank you.
Okay, now there is a question from Alexandre Toubiana.
Yeah.
Hi, Danièle.
Hi.
Thank you very much for the talk. I have a very naive question. In fact, it's just if you go to the plot with the different detectors. Yeah, the previous. Yeah.
Oops, sorry.
How does it come that? No, sorry, the one you were before, with the omega. Yeah. Just how does it come that Lisa is below ground-based detectors? What exactly is in the y-axis?
So I didn't make this plot. What's on the y-axis is here, right?
Yeah, but because I mean, is it? But for the detectors, are you plotting? It's not the sensitivity, right?
No, it's not the sensitivity. It's not quite the sensitivity. It's related to the sensitivity, but there are some factors of F in them.
Okay. Yeah.
Yeah.
Thank you.
Thank you. Any other question in the audience? If not, no, I cannot see any. So we can have indeed a short break. So
I have a question, please.
Yes, please raise. You can. Yes, okay.
Please go ahead. Yeah.
Thank you. I was wondering about this figure concerning inflation, matter, inflation radiation and matter. I would like to know if it's normal that radiation comes before. Yes, this one. If it is normal that radiation comes before matter, since perhaps after inflation, the universe was not cold enough in order to let the radiation escape. So perhaps behind inflation, we could have matter first, and when the universe becomes cold enough, then let escape the radiation.
Yeah, so you're right. You can have a short period of matter domination after inflation from reheating or preheating. You're right. But the dominant period is the radiation era. I mean, the one which is dominating the observations. But you're right. Yes, there could be a short period of matter domination at the end of inflation.
Okay, so if we take into account this part of matter, could this modify some properties of stochastic gravitational waves inside this super horizon region?
So I think the answer would be that you would, if you were actually looking at a stochastic background generated from preheating, which people do, and that's where that effect would come in. But the sources which I'm going to look at here are all after the preheating period, well in the radiation era.
Okay. Thank you so much.
Okay, no more question. Then therefore we can have this short break. So how long do you want to break?
Maybe 5 minutes.
Okay, 5 minutes is good. Then we
Okay.
recombine at 5:15, right?
Yep.
Okay, see you then.
Bye. Okay, so now I want to carry on, but specify the source, or think a little bit more about the source. So again, I've got the plot down here on the right-hand side. I want to think about a source which is acting in the radiation era. And in fact, in the end, I'm going to limit myself to a source which acts during a short period in the radiation era. And I want to see how far we can go without actually specifying in detail the properties of the source. So let's go ahead. So as we've already seen, we can take the Fourier transform of the anisotropic stress, so the transverse and traces part here of the anisotropic stress. Take its Fourier transform and decompose it into the two polarization states, which I remind you, this was the source on the right-hand side of our perturbation equation. And just as for the metric perturbation, we're going to describe the source stochastically. So here's its two-point correlation function, which has a similar form to what we saw previously. There's a delta k minus q because of homogeneity and isotropy. The delta r minus p, rp because of non-polarization. And this is going to be the absolute crucial quantity in any calculation of the stochastic gravitational wave background. This crucial quantity is the unequal time correlator pi of these two quantities. So these are evaluated at two different conformal times, tau and eta. And as we'll see, this is the quantity which is going to determine the shape of the stochastic background for your source. So please bear that in mind, the unequal time correlator of the anisotropic stress. Good, so let's go back to our perturbation equation, so which is sourced by pi r. Let's do our standard change of variables, which is here, so that we can rewrite this equation in the following form. And our aim is to solve it with the source, so as to find the spectrum. Oops. Okay, so I'm going to assume, as I already said, that the source acts for a finite time. So here's the picture on the right-hand side. And so this equation, you can simply solve it with the green function. So here's a solution for times between eta initial, when it turns on, and eta final, when it turns off. So h and I'm assuming the radiation era, so for eta less than eta final, it's given by this integral. You see the a cubed from here and the Green's function for this operator. Now, after the source is turned off, so for times bigger than eta final, we already know the solution, at least if we look on sub-horizon modes. We wrote the solution down last time, a few slides ago. So that was a constant times e. Well, before I wrote it e to the k eta, let's now decompose it into sine and coses because of this sign here. And it's very easy to match these two solutions at eta equals eta final and find the constants here in terms of these integrals, right? It's a straightforward matching between here and here at eta final. So here are the solutions for the constants, well, k-dependent constants A, R, and B, R in the radiation era. So I'm going to copy those again on the next slide. They're up here. And I've also copied the formula for the definition of the unequal time correlator of the anisotropic stress. Oops. Now, we already saw, again, previously, that once we have free modes, which is what we're looking at after the source is switched off, we've already calculated this correlator on subhorizon scales, and we saw that it was given by 1 over a squared, which is now, I'm evaluating this today, so 1 over a0 squared times this, sorry, I should have put rad on the top here for both of them, times these two two-point functions. And now we can calculate those two-point functions because we have the expressions for A and B here on the right-hand side. So if we calculate them, we'll get the expression for HC, if you remember the definition of HC, which we can then substitute in here to get the power spectrum today for modes which are inside the horizon, right? So where does this term come from? So let's try and see where it comes from. So it comes from here, essentially. It's this HC squared, which comes from here. So what happens is, so if you substitute the A's, right, for the A's, you see that you have two integrals. So there's an integral which I'm writing as d tau times a cubed here. The second term here has a d psi by times a cubed. And then this will be multiplied by a factor of sine k tau times sine k or p psi from the second integral. So product of sines times a pi squared, pi r squared. This one will be a product of coses times the same pair of integrals. And a sine with a cos becomes a cos times the difference between the two. And it's multiplied by, if you think about it, exactly this correlator with the various factors of k, which should work out as I've written them here. So that's the origin of this cos of k minus psi, and then multiplied by the unequal time correlator. And so this is precisely what I was saying here before, that there's this unequal time correlation function pi of your source, which is going to define or determine your gravitational wave background, the energy density power spectrum. So this is a crucial quantity to calculate if you have a source in mind. So there's one case in which we can actually try and estimate the size of this thing. So estimate the size of pi. So here's my simple example. So I've just copied down the same expression to start with in blue. Okay, and the simple example I'm going to consider is, well, I've tried to draw it again on my diagram. So I'm firstly going to assume that this period, so during which the source acts, so eta initial to eta final, is very, very small compared to Hubble time. So let me associate eta initial with eta star, so the time at which the source acts. And I'm going to assume that delta eta, so eta final minus eta initial is very small, which means that A here, the scale factor, I can neglect the variation of the scale factor in this integral and just replace it by the scale factor at, let's say, the eta initial. So then this term I can replace by A star times delta eta. And similarly for this term, A star times delta eta. Then I'm going to assume for simplicity that the source is like a top hat, if you want. It's constant over the period of time delta eta, and otherwise it's 0. So I'm going to replace this unequal time correlator by simply a top hat function, if you want, so some function of k, which is valid over a time delta eta. So it's non-zero over time delta eta. And then I'm going to look on scales k, or on scales, so this is my dotted line, right? Scales k, such that k eta n is much smaller than 1. In other words, I'm looking at scales which are outside the horizon at this point, eta, when the source is acting. So to summarize this solution, which I've written down, assumes that k eta 0 is much bigger than 1. And I'm going to look at it in this region. The solution which I'm going to be looking at should be in the region between well, as indicated by my red arrow here. Right, so how does this expression simplify? So again, I've written down the blue box this is a range of k's which I'm, oh yes, sorry, that's what I wanted to say. If I make this approximation, why am I doing that? It's because then I have cos of a small quantity which I can replace by 1. Okay. So I do all these, I make all these simplifying assumptions. So A, I replace by A star. So this becomes essentially a factor of delta eta times H star squared, because there are 2 of them. Then I can replace this. So this I've done something a bit, just, it looks complicated, but it's not at all. I've rescaled the anisotropic stress with a factor of the energy density rho, because as I said right at the beginning, I can then use the Friedman equation to replace the G times, essentially G times rho gives me a factor of A, which I'm going to use to cancel out other factors of A. And if you do all of that, and you're very careful, and if I didn't make a mistake, then you find that the energy density, so omega gravitational waves, is given by this expression. And this is what I now want to look at it, because I want to think about the orders of magnitude. So what kind of orders of magnitude do we have here? So let's say that I actually want to detect a stochastic gravitational wave background, then this left-hand side would need to be about of order 10 to the minus 11 at least, because we want to have a detection in the future. So that is what the kind of order of magnitude I want for the left-hand side. Now, all of these quantities here, you can calculate. I mean, so far I've neglected any variation of the number of degrees of freedom. In fact, this term is, let me take it to be of order 1, but you can calculate this quantity to be of something of order 10 to the minus 6, approximately. And so if you want your source to give you an observable stochastic gravitational wave background, then you need this whole remaining part to be of order 10 to the minus 5. So if it's of order 10 to the minus 5, then this term is better not be too small, which means that your process had better not be too slow. And you want this term to be as big as possible. So you want to have a very anisotropic process. It's only very anisotropic processes which have the chance of detecting, of generating a detectable gravitational wave signal. And then the last comment that I want to make about this, this simple example is actually the shape of the spectrum. So there's one last thing that we know about the shape, and it comes from the fact that our unequal time correlator of the source, it had better be independent of k for large enough scales, because our sources have to be uncorrelated. So if it's independent of k for large enough scales, then we know that this quantity on large enough scales has to go as k cubed. And so if this quantity goes as k cubed, the p also goes as k cubed. And so we can, we arrive at the conclusion that the spectrum omega gravitational waves goes as k cubed if we're looking at large enough scales. So that's a bound of causality, which is actually very useful, because if you calculate when you calculate the stochastic background from different sources, it's easy to make a mistake. So one good thing is to check the scaling that you have for large enough scales, so small enough k. Okay, so now those were simple examples. I now want to go into a little bit more detail about some more realistic sources. So the physics which can happen around the electroweak phase transition to start with, and then I'll go on to cosmic strings and then on to inflation. So the electroweak phase transition. So here I've drawn some bubbles. Why have I drawn some bubbles? It's because if the phase transition, and this is an interesting question, but if the phase transition that we're studying at energy scales of the order of the electroweak phase transition is first order, then it can lead to gravitational wave production. So let me remind you, for those who may have forgotten, what a first order phase transition is. So very schematically, if you draw the effective potential for your field theory as a function of field phi, for example, at different temperatures, so the finite temperature effective potential, then at the critical temperature of the phase transition, in the first order phase transition, there are two degenerate vacua separated by a local maximum. And then as the temperature drops, this the global maximum develops at some value of the scalar field. And so to go from the false vacuum at phi equals 0 to the true vacuum state at lower temperature, then the field has to tunnel through this potential, and this tunneling leads to the formation of bubbles of true vacuum inside the false vacuum. So it's the analogy would be if you think about water boiling, right? There are bubbles that are in the water, and then the bubbles expand. So that's precisely what happens. So these bubbles of true vacuum expand in the false vacuum. One bubble by itself, because it's spherically symmetric, because of Birkhoff's theorem, there will be no gravitational waves emitted by a single bubble, spherically symmetric bubble. But once the bubbles start colliding, then spherical symmetry is broken, and gravitational waves can be produced. In fact, they can be produced in this picture in a number of different ways. When the bubbles collide, because that breaks spherical symmetry. Now these expanding bubbles also perturb the plasma in which the plasma in the universe at that time, and they can lead to the generation of sound waves and turbulence in the plasma, and turbulence can also, and the sound waves also can lead to gravitational waves. And there could be also primordial magnetic fields. So in other words, the sources for the collision of the bubble walls, there's an anisotropic stress from gradients of the scalar field, because the scalar field, it goes from phi equals 0 outside, right, to some non-zero value inside. There are gradients of the scalar field across the bubble wall. So that's the collision. From the collisions of bubble walls, you have an anisotropic stress. The fluid motion gives you an anisotropic stress from, it's just the anisotropic part of the stress energy tensor of the fluid. And then if you have electromagnetic fields, you can have also a non-zero anisotropic stress. So these three physical phenomena can generate gravitational waves in a first order phase transition. So if you want to calculate the final spectrum, you have to calculate the contribution from the bubbles colliding, calculate the effect of turbulence from the second one, and then possibly from any electric and magnetic field. So that's a complicated problem, and it has a number of relevant parameters. So there's the temperature of the phase transition. There's the duration of the phase transition with respect to the Hubble time, which is basically what I was calling epsilon star. There's the strength of the phase transition. And then there's the speed at which these bubble walls expanding, because the faster they go, as you might expect, the more they're going to stir the fluid, and the more there'll be sound waves and turbulence. So if you put all of that together, and it's a complex problem, you can calculate the dependence of these three sources on the four parameters and predict your signal. So here I've taken a plot from a paper by Pierre and collaborators for LISA. Why for LISA? Because I already explained to you that the characteristic frequency for the energy scale of the electroweak phase transition falls slap bang in the sensitivity band of LISA. And here you see the result. So there's a contribution from the collision of the bubble walls in blue. There's a contribution from sound waves, and there's a contribution from turbulence. And the sum, which has the right frequency dependence on small scales, is here. So that's an example of a source which can give a stochastic gravitational wave background. Now, I guess the more particle physics people amongst you would say, but what you're talking about, the electroweak phase transition, is probably not first order, and that's true. In the standard model of particle physics, the phase diagram was calculated by Keijo Kayenti and other people in the 90s. And if the Higgs mass is, the Higgs mass is 125 GeV, then the electroweak phase transitions is actually a crossover, and it's not first order. So if it's a crossover, then it doesn't go through bubble nucleation. And in fact, it's a much smoother process, and one doesn't expect any significant gravitational wave production. So then the question is, why bother? Why do all of this? And the answer is that the electroweak phase transition can actually be first order in many extensions of the standard model. So if a signal of this kind were observed in NISA, then it would be telling us about the electroweak phase transition in extensions of the standard model. So it's a way of probing particle physics. Okay, so the electroweak phase transition was an example, or these bubble collisions is an example of a source which lasts for a short time. How about an example of a source which lasts for a much longer time? And the example here is that of cosmic strings. So cosmic strings are topological defects. And maybe they sound elaborate, but in a sense, they're not elaborate, because topological defects exist whenever you have a symmetry breaking phase transition. So let's say your first symmetry, high temperature, is G, and the symmetry in your theory is broken down to H. And you can show that there will be line-like defects as long as this is mass, but it doesn't matter, as long as the vacuum manifold is non-contractible. So that sounds complicated, but there are examples of line-like topological defects everywhere in nature. So not just in high-energy physics, but in all sorts of other branches of physics. For example, in condensed matter physics, there are vortices, so the equivalent of cosmic strings of vortices in helium, so in superfluids such as helium-4 and helium-3, where you have phase transitions of this kind. In superconductors, where you have a U1 which is broken, which also gives rise to vortices. In pneumatic liquid crystals, if any of you have a kind of 80s or 90s watch with a screen made of pneumatic liquid crystal, when you can also have strings and pneumatic liquid crystals, and they're here. So topological defects, in particular cosmic strings, might sound, let's say, unusual, but I think they're not unusual in the sense that it's physics which is seen at many different energy scales, from the lab to all the way to the early universe. So what do we have in mind, indeed, in the early universe? We have in mind strings which are formed in a symmetry breaking phase transition. And there are different ones that you could have. You could be talking about grand unification, right? At about 10 to the 16 GeV. Or you could talk about strings formed at the end of, in more extended models, hybrid-like inflation, or you could even talk about brane inflation if you wanted extra dimensions. But there are arguments around that show that many of the phase transitions that one would expect in the early universe all come with this condition which is satisfied, which means that strings must form. So if you accept the fact that there may be symmetry breaking phase transitions in the early universe that can form strings, well, the thing about those strings is that they can't disappear because they're stable. The reason why they're called topological defects is that they're stable for topological reasons. And that is that once you have these strings formed in the universe, they might lose energy, but they can't disappear entirely. So if they're formed at grand unification or at the end of brane inflation, then they're still here today. So people have worked on strings for a long time. Strings have not been found as yet, despite people looking for them, so in gravitational waves, as we'll see. People are looking for their effect on the CMB, because they, in fact, a string will, you would see it in the CMB because it basically it bends photons, and so it affects the temperature and isotropies. Strings also generate B modes, so not only inflation generates B modes, but strings do because strings generate vector modes. Strings can give rise to lensing, so this would be on the right-hand side is a typical image of a galaxy lensed by a string. You can kind of guess where the string is. And they give rise to other effects, electromagnetic effects. So the constraint on strings, so today is this one. So I want to explain what these quantities are. So mu is the energy per unit length of the string. And G is Newton's constant. So this quantity is dimensionless. So the constraint today is that G mu is of order 10 to the minus 7. So just to maybe to try and fix ideas, let me give you a specific example of a theory which would give rise to a string. And the specific example is the abelian Higgs model, so with the Mexican hat potential, which you can see here on the right-hand side. So the Mexican hat potential has a circle of vacuum, which is in red. And so when you go through a phase transition, you start off with a potential which is symmetric. The field has to go from the top, and in each part of the space will choose one vacuum, some point on this circle. And you can have a situation, and generically will in different parts of the universe which are not causally connected. So you can have a situation in which one part of space, physical space, the field rolls down, let's say, to this value on this point on the circle. You can have another region of space where the field rolls down, let's say, to this other blue point. And you can have a third region of space where it rolls down to a different point on the vacuum manifold. So all of these points are on the vacuum manifold. They all have the same VEV, but they have a different phase. And so you can have a situation where when you go around a circle in physical space, you actually end up going around a circle of the vacuum manifold. So everywhere you're on the vacuum, but you have a different angle on the vacuum if you want. And if you then take that red circle in physical space and contract it, then you can see that the angles all have to vary as you go around that point, which means that in the middle, the field must be there. If the field is continuous, the only place where it can be in the middle is sitting at phi equals 0. And if it's sitting at phi equals 0, it has larger energy than when you're outside the string where you're on the vacuum manifold. So essentially what I'm saying is that you have a point in the middle where the field is sitting at phi equals 0, so you have more energy. And if you think about it, then in fact, if you think about it, that will correspond to a line in space where the field is sitting at phi equals 0 inside the line, inside a certain region anyway. And phi is equal to eta, so the vacuum, so it's on the VEV here, outside. And so you therefore have more energy. You have energy which is trapped on the line. So that's what a string is. And that's exactly what a string is in a superconductor. It's exactly what a string is in a pneumatic liquid crystal. They all have exactly the same property. They're all there for topological reasons, because you have a vacuum manifold which has non-contractible loops. So here's the mass of what I said. That doesn't really matter. The important point is that you have this region of space where you have more energy density. And so you can talk about strings. These strings are characterized by an energy per unit length, which is what I called mu earlier on. Now these strings can either be closed. So in other words, this could join up. You could go around in a loop and join up, in which case we call them loops. Or they can simply be random walks across the universe with no ends. They can't have ends because that would cost an infinite amount of energy, kinetic energy. So strings are either infinitely long or closed loops. Right, so why am I talking to you about strings? Well, let me carry on first, because they're going to produce stochastic gravitational wave background. But let's think a little bit about the width of our strings here, the width of this green line, the width of the region where phi is equal to 0. And basically from dimensional analysis, the width of the string is given by the inverse mass scale associated with the phase transition. And you can convert that into a distance for an energy scale of 10 to the 16 GeV, for example. And it gives you a string of width 10 to the minus 32 centimeters. Right, that seems very small, indeed. You can also calculate the energy per unit length, mu, which for dimensional reasons has to be given by essentially the mass scale squared. And if you work out the dimensionless quantity, which I said g mu was dimensionless, it's of order 10 to the minus 7. So those numbers may seem small, but that's a question of units, because it's you can do the simple calculation. If you take a length of string, the width of the sun, okay, the radius, the diameter of the sun, and of this width, it has about the same mass as the sun. So in fact, they're very, very narrow, but they have a huge amount of energy in them. And that's why they can have interesting observational consequences. Before we get there, as you can guess, given this small width, many models assume that the strings are infinitely thin. So you describe them by the so-called Nambu-Goto action. But in a sense, the beauty of these cosmic string models is that they only have one parameter, which is this energy per unit length, mu. Now, to make predictions from these objects, particularly for the stochastic gravitational wave background, you need to know how the network of strings, of which here's a picture, evolves in time. So this is a network of strings that contains long strings, so this is a horizon size. So these long strings have a length which is larger than the horizon. And the little blue ones are little loops. And why do little loops form? Little loops form because when a string dynamically bends across itself, in fact, it will chop off a loop. So it's a process known as intercommutation. So the long and the short is that a network of string will contain horizon-sized loops, so closed loops which are basically smaller than the horizon, as well as these very long strings which cross the horizon. And you can study the evolution of this network. It's kind of complicated because there are lots of different scales in the problem, but you can show that these networks sort of evolve to an attractor solution, a self-similar solution, in which the energy density in strings is a fixed fraction of the energy density of the universe, and the strings will stay around, diluting themselves for all times. So where do gravitational waves come in? They come in a number of different ways. The first thing is that these loops, they can, just from the dynamics of the Nambu-Goto action, you can show that they can instantaneously at different points in their evolution basically go at the speed of light. So those points have huge Lorentz factors and they can give rise to the emission of gravitational waves. And they also have other interesting points, which are discontinuities in the tangent vector, which are known as kinks, which can also produce gravitational waves. And in fact, there are a number of experiments, so in particular the LIGO-Virgo collaboration, that look for cosmic strings in two different ways. So for strings which are close by, you can look for bursts of gravitational waves from these so-called kinks and cusps. So again, a cusp is a point that goes at the speed of light, and it emits a burst of gravitational waves. And a kink is a discontinuity in the tangent vector of the string that also emits gravitational waves. You can calculate the waveform of that. It has a characteristic form, and you can look for it in the data. And that's what the LIGO-Virgo collaboration does. But there's another source of gravitational waves, which is the one which interests us here, which is a stochastic background. And the stochastic background is produced by these loops, because all these loops, in fact, also oscillate. They have a periodic motion, so they oscillate in time. And because they oscillate, they emit gravitational waves, and eventually the loops will disappear. But as I said, they're sourced because they're also produced by the long strings that are also intersecting each other. So the stochastic background is the sum of all the gravitational waves emitted by all the loops through the history of the universe as the network evolves. So the crucial quantity, if you want to estimate the gravitational wave background from strings, is the number density of loops at a time t. And unfortunately, this is where the slightly unfortunate point is that there's no real agreement at this point in time as to what this number density looks like, because this process is so nonlinear, it's very difficult to calculate. So that's why in the following, I'm going to show you some predictions for the stochastic background for two models, which I don't want to go into the details of the model. I've just called them in a rather unpleasant way. I've just called them Model A and Model B. So they have Model A and Model B simply differ by the properties of this loop distribution on, in fact, just for very small loops. They agree for large loops, but for small loops, they disagree. So here's a prediction for the stochastic gravitational wave background as a function of frequency for Model A. And the only thing which is varying in between these different curves is the one parameter of the theory, which is the energy per unit length of the string, which I remind you is related to the temperature or the energy scale of the phase transition which produces strings. So here's the sensitivity curve of LISA. Here's the sensitivity curve of pulsar timing. Now this plot was generated before the result from that I outlined earlier, right? The constraint I outlined earlier, the nanograph constraint. So let me not talk about it for now. What I want to show to you, what I want you to take away from this plot is that the lighter the strings, so the smaller value of G mu, obviously the more the spectrum, the amplitude of the spectrum goes down. But otherwise, it's a very broad spectrum, okay, which spans a huge number of decades in frequency. So not only can it be constrained by LISA, but by pulsar timing and by LIGO up here. And I'll show you the results for LIGO in a second. So this was for Model A, and now I'm going to show you Model B. So the different loop distribution, and as you'll see, the results unfortunately are quite different. Okay, so these are for the same values of the parameters, but the predictions are unfortunately quite different because Model B ends up having a lot more loops, so the signal is a lot higher than for Model A. So as I said, and I'll just repeat again, the unfortunate situation with cosmic strings at the moment is that we have two models. We're not quite sure which one is right. And it's difficult to put constraints on these theories because the predictions are quite different for the two models. But of course, one can try anyway. So this is the similar set of plots, different color scheme because it's a different paper. This is from the very recent paper from the LIGO collaboration on constraints from cosmic strings. Again, there's Model A and Model B. And again, it's the same plot, omega gravitational waves as a function of frequency. And again, for different values, well, actually, this is not quite the case. This is, let's just look at one of these curves for a given value of G mu. And so from the constraint on the stochastic background that LIGO has put out, you can put a constraint on the value of G mu. And unfortunately, I didn't put it here. Sorry. Yeah, you should look at this. NK is the number of kinks I don't want to talk about. Let's just look at the point NK equals 1. So the constraint for Model A is that G mu has to be less than of order 10 to the minus 8. And for Model B, the constraint is that G mu has to be less than something of the order of a few times 10 to the minus 14. So depending on which model you believe is true, but you see that the stochastic gravitational wave background generated by strings is being, so the observations, or the lack of observations, if you want, are putting a constraint which is getting stronger and stronger on G mu. So it's getting stronger and stronger on the temperature at which of the phase transitions which should have formed these strings. So in other words, what I'm saying is that we already know that strings can't have been formed at a phase transition at an energy scale of the order of the gut scale, so 10 to the 16 GeV, for the simple reason that it would give you a G mu. Gut scale strings would have G mu of order 10 to the minus 7, and 10 to the minus 7 is already ruled out, whatever the model. So we already know that if there's a symmetry breaking phase transition in the early universe that leads to strings, then it must occur at an energy scale which is lower than, well, a number which unfortunately is model dependent, but is certainly lower than a G mu of 10 to the minus 16 GeV. An energy scale of lower than 10 to the minus 16 GeV. Okay, I was expecting to have a 2-hour talk, so we will go back to inflation in a second. So let me come to the conclusions of this first part. So the stochastic gravitational wave background, as I explained in the last lecture, provides an absolutely wonderful means with which to probe the early universe. But in a sense, by construction, because we're looking at physics at such high energy scales, the predictions are speculative. If it's the electroweak phase transition, for example, we don't quite know what physics is going on. We don't know if it's first order or not. For cosmic strings, we're talking about symmetry breaking phase transitions at scales. We don't know if they exist. But if they do, then, and if we observe a stochastic background, then we have a wonderful way with which to probe fundamental physics. And it could be that there are discoveries which will be around the corner. I hear noise. Is there a question?
Yeah, there is a question.
Okay,
so,
please.
From Alexandre to Biana.
Oh, okay. Well, maybe you want to finish first, Danièle. I don't know.
Yeah, okay, good. So, yeah, so basically I'm just saying what I already said. The electroweak phase transition is at the limit of tested particle physics. But any gravitational wave signal that were produced could be accessed by LISA if its amplitude is big enough. This requires models that go beyond the standard model of particle physics. And so, as I already said, essentially what we're doing is tests of these models, which are complementary to particle physics colliders. Cosmic strings, I think, are theoretically well motivated. They're basically the analog of physical phenomena that occur at many different energy scales. Their signal spans many decades in frequency, and they can be accessed and constrained by many different experiments. But unfortunately, there's still work to do, actually theoretical work to do on modeling cosmic strings because of these. You don't understand the loop distribution 100% yet. And then if I'd had a bit more time, I maybe would have said something about inflation, which of course is extremely well motivated in the standard cosmological scenario. But if you do the calculation, it leads to a stochastic gravitational wave background, which is absolutely tiny. And so for it to lead to anything which is observable by pulsar timing, LISA or LIGO, you would need to actually modify the standard single field slow roll inflationary models. But that's a different, maybe slightly different subject. Sorry, please, Alexandre.
Okay,
yes.
So now go on, Alexandre.
Okay, thank you. So could you go back to the predictions for LISA, please? Yeah, fine, thank you. So do you know how does it compare to astrophysical sources? I mean, the scale is hard to guess here, but it seems that it could be very loud.
So this is certainly not from astrophysical sources, right? This is obviously just from the string network.
Yeah, but I mean, the amplitude because it seems here that it could, I mean.
Why do you say this is loud? This is the sensitivity band of Lisa, right?
Yeah, but so I'm saying I'm not used to this kind of scale, but it seems that for instance, in the more energetic model, wouldn't it be covering, for instance, all the massive black hole mergers or?
No, I don't think so. Okay. I don't think so. In all of this, and because I'm a theorist, I have to say that in all of this, I'm assuming that somebody who can calculate the astrophysical background has subtracted it already, and I'm only interested in the cosmological background that's left, and that's what I want to constrain.
Okay. Okay. Yeah. Well,
I don't think it is. Well, I think the astrophysical background is extremely loud. I think it's probably louder than this, is my impression. Unless you take, so you see G mu, in fact, now maybe I can have a better answer. G mu, as I already explained, is also constrained by CMB observations, because these strings, because they have such a large energy density, though it looks small in these units, they affect the temperature, they give rise to temperature fluctuations in the CMB. And that constraint puts G mu to be less than about something of the order of 10 to the minus 7. And I would suspect that that's already much lower than any astrophysical background, is my impression. But I would need to think about it.
Okay. And so just also in general, in fact, we would expect that all the possible sources you mentioned would superimpose, right?
Yeah, right. It would be a sum of all of them, yeah.
And so do you know exactly if it would be possible, so if you just consider the cosmological background, to extract the contribution of these different sources?
So I guess you'd have to compare the shape of the spectra, right? To see if you could, to see how you could extract them. So the big difference between the spectra from strings is that you would really, because they're over many decades in frequency, you'd expect to see them in all experiments. If you see them in one, you're probably likely to see them in all. Whereas I guess that's not true for the electroweak phase transition, right, with bubbles. So I suspect there would be a way of differentiating them. But I think you'll be lucky. Maybe first we have to see at least one signal, right, from cosmological sources.
Okay, yes. Thank you.
Okay, so there is now a question from Il-Sang Yoon.
Hello. Thank you very much for this nice presentation. I'm wondering about the purely observational point of view, whether we can characterize the shape of the power spectrum, for example. To do that, do we know what spatial, the resolution, or in the other words, how accurately we can localize the stochastic background signal? Is it possible, if it's not now, but if it's possible someday, if we have a different experiment to actually localize at enough spatial scales that we can characterize the power spectrum?
So, I don't think I'm the right person to answer that. Honestly, I don't know. Maybe somebody else knows. Somebody else know? Guillaume, maybe you know?
Sorry, I was doing managing stuff and I could not hear the question.
Can you repeat the question?
Yeah, basically how to characterize the shape of the power spectrum using the observations of this stochastic background of gravitational emission. Then how accurately do we need to localize the emission? So is it possible with the future experiment, or is it still daunting task?
What do you mean by localize? I'm not sure.
Yeah, I'm talking about like the analogy of the CMB fluctuations, right? So we characterize the power spectrum using
yeah, so if your question is, can we, in the future, can we measure sort of deviations from,
you're right,
from isotropy?
Yeah, I think there are.
Then, right. Then people indeed are thinking about that. Now, whether it's not clear to me, I think it's already hard enough measuring the homogeneous and isotropic component, right, before looking at fluctuations. But it's indeed certainly something that people are looking at.
Okay.
Okay, there is a question or maybe a comment from Jacopo of Magali.
Yeah, hi. So my question would be, yeah, it's probably very naive, but since, as you say, like with this cosmic string, you have a spectrum that span a broad range in frequency space. So in principle, the question is, can you solve the dispute among the theoretical dispute among model A and model B if we see like the signal in difference experiment?
Sorry, so is your question, if you see the signal in different experiments, can you distinguish between model A and model B?
Yeah, that's the question.
Yeah, so the answer is probably yes, I think, because yeah, so if you in the LISA band here, in fact, whether you're looking at model A or model B, you can see that any value of G mu above 10 to the minus 7 should be visible in LISA, right? Mm-hmm. If you look at these two, right? 10 to the minus 17. So 10 to the minus 17 basically just grazes this point, right? For both models. But the same is not true in the LIGO band. So in the LIGO band, model 2 is already predicted to produce a signal which is visible, which is why there are strong constraints on G mu. So you could have a situation in which, if you had a situation in which LISA sees a signal from strings with this shape, by the way, and so does LIGO, then that would point more to model 2.
Okay, that's clear. Thanks.
Okay, there is now another question from Germano Nardini.
Hi.
Ciao.
Maybe a question or a comment, but Danny, can you go back by one slide, please?
Sorry, can I go what?
Back by one slide back. Yeah. So concerning maybe this question, if you're not considering other possible stochastic backgrounds, here just in LISA, the signal to noise ratio is so strong that you can reconstruct the power index of the signal. Mm-hmm. So within LISA, if you're not considering other possible inflationary signals, you should be able to distinguish between model B and A.
Because of the slope, you're saying, right?
By the slope, yeah.
Yeah.
Okay, yes.
If G mu is big enough, yeah. Mm-hmm. Thank you, German.
I cannot see any new question for the moment, so maybe I will ask one. What I would like to know what happens if we go beyond the Nambu-Goto strings. So if we have more realistic strings coming from, great unification and symmetry breaking from this kind of thing. So what would it change anything to the current knowledge we have?
So it depends what you mean by more realistic, I guess.
Yeah, I don't know myself. I mean, I don't know how much we can expect that the real strings in nature are Nambu-Goto strings.
Well, as I tried to argue, at least as it comes to the width of the string, I think it's probably fair to take them as infinitely thin, because they really are very narrow relative to the Hubble scale, right? But then there are two other important possibilities, which is that since basically it's the Higgs field which is forming the string. Okay, this is the Higgs field. And of course, in many of those grand unified theories, the Higgs field, okay, it's more complicated than this, but it's coupled to other fields. And the result of that is that you can actually have other modes which are confined on this string. And those modes can propagate along the string and so give rise to currents, which can be charged or not charged. But if you have a current on a string, that can change the dynamics of the string. So it can actually change its action and add some other terms, which there's a very interesting effect of that is that if you have a current on a closed loop such as this one, This one, if it didn't have a current, what it does is it oscillates because its tension is pulling it in. So it actually just oscillates in and out, emitting gravitational waves. But if you have a current, then it's basically there's a centrifugal force which is going to try and counteract the collapse from the tension, and it can lead to in fact stable equilibrium loops, so loops which are basically fixed and stable and don't oscillate, and so they're not emitting gravitational waves, but they're still there in your network. And those loops, in fact, you can show that they behave like matter. And so some people have tried to argue that they can act as a source of dark matter. So indeed, if that was the direction of your question, then there's a possibility that strings can not only produce a background of gravitational waves, but they can also be a source of dark matter.
Okay, thank you. So, new questions in the audience, perhaps? No, I cannot see any reaction for the moment. So, Danièle, did you have anything to tell us beyond this about inflation?
Well, if there was if anyone is interested, maybe I can leave inflation because I think Jan Manuel may be talking about inflation tomorrow. The only other thing which I would have been happy to, because I know there are people who are in the audience who might be interested in it, is to go to the thing which I didn't have time to talk about so regarding late time cosmology and what you can do with individual sort of gravitational wave signals of the kind of GW 170817. So how you can test theories of modified gravity. So I don't know if anyone's interested in that. I'm happy to mention a few words about that.
Well, I would be interested personally.
Okay.
Yes, and you have some comments in the same direction.
Okay.
There is a question before that. Does the intercommutation process happen in only one direction, from the string to loop only?
I'm not sure quite what string to loop means, but no, it's more general. If you have two strings that collide with each other like this, then they'll always interchange, so intercommute. So they'll join up in the opposite direction, if you see what I mean. So those two strings can be long strings that just intercommute, or it can be one string which bends back on itself and intercommute.
Okay, thank you. I think you can go ahead then, Danièle.
Okay, so in the last lecture, when we were talking about about measuring the Hubble constant amongst other cosmological parameters with the individual gravitational wave signal so the gravitational wave signal from individual sources, so binary neutron stars or binary black holes or neutron star black holes, we assumed that general relativity was the correct theory of gravity. And so again, just to repeat, the idea was that from the waveform, which is proportional to 1 over the luminosity distance, you extract the luminosity distance to your source. From an electromagnetic counterpart, just to be simple, let's assume there's an electromagnetic counterpart. You measure the redshift, and so from those two, you can extract the Hubble constant. But the assumption was that general relativity is the correct theory of gravity. Now, many people, and indeed you've had lectures on modified gravity, are interested in theories which are not general relativity or beyond general relativity. So how can you test those theories with binary system? So I'm sure Shinji Mukoyama gave you some motivation for modified gravity. Let me give you mine, which to understand GR better. Another motivation is that it's all very well assuming general relativity is true on all scales, so galactic and cosmological, but it hasn't been tested on those scales. So maybe it's a bit of an extrapolation to assume it's true on all those scales. And of course, perhaps the biggest motivation is to say that let me get rid of this dark energy and explain late time acceleration by modifying my theory of gravity. So if I make gravity weaker on cosmological scales, then in principle I might be able to explain the accelerated expansion without dark energy. So those are some of the reasons why one might be interested in looking at theories of gravity beyond general relativity. And indeed, that's what a huge amount of work has been involved in. Now, your models, however, have to satisfy at least some constraints. Any modified gravity theory has to reduce to general relativity on the scales in which we've tested general relativity, so on the solar system scales and smaller. And at the same time, you also want it to lead to significant differences with general relativity on large scales. And it turns out that's not so obvious. If you want to reproduce general relativity on small scales, often that means that you have negligible differences from general relativity also on large scales, in which case you're a bit stuffed because it doesn't solve this problem in any way. And of course, there's another constraint which is critical, which is that your theory has to be mathematically consistent and stable. And that's not easy to do because you often have these ghost-like instabilities, as I'm sure you heard about in the other lectures. So your conditions that your modified gravity theory, you'd like to, well, they must be satisfied. These motivations you'd like, well, at least this one you'd like to be able to solve this problem. But first, there's this lovely theorem of Lovelock, which tells you what at least you have to do to modify gravity. So Lovelock's theorem says that general relativity is a unique theory with second-order equations of motion, local second-order equations of motion for a metric in 4 dimensions. So if you want to modify gravity, then that tells you that you have to, there are 4 things you can do at least. You have to go beyond the metric, so add extra fields, or you have to allow higher order derivatives, which, as I'm sure you heard about in the other lectures, gives you all sorts of problems with mathematical stability, or you can work in higher dimensions, or you can allow non-locality. So you have to break the postulates of this, the requirements of this theorem. So there are a lot of different things around. Okay, there's some of the different possibilities for how to modify, ways of modifying gravity, adding extra fields, which could be scalars, vectors, or tensors. Adding extra fields in the form of adding a mass to the graviton. Or you could have non-local theories, which some of the people in the audience I know are working on. Or you could work in more than 4 dimensions. So there are lots of different theories. How can you at least try and see if you can test some of the general principles at least? So this is a slide which I showed you last time, which was, so last time I explained to you that if you wanted to calculate the waveform for your binary system at some large cosmological scale from the binary, the simplest thing to do is to take the waveform in the Minkowski space solution. So when you're close to the source, so in the local wave zone of the source on scales which are large relative to the source, but small relative to the Hubble scale. So you know the solution here, and then propagate it through your expanding universe to the observer. And if you want to, you can do the same procedure in modified gravity, but the difference will happen not at the local, well, it could happen locally, but let's assume that general relativity is true in the close to the source, so that the expressions we had for H plus and H cross are true close to the source. What will change though is generally the propagation of your solution from the source to the observer. Now, there are lots of ifs and buts in what I've said. Some of these theories have extra degrees of freedom. Some of them have more complicated things, but certainly my assumption is going to be that close to the source, general relativity is correct at small scales. Then you can just modify the propagation of your solution, your waveform from the source to the observer. So in other words, I want to replace the left-hand side here. This was in general relativity. Gravitons were massless, so they go at the speed of light. I want to replace the left-hand side by something a little bit more complicated. So here's my source. It can emit gravitational waves at different times. So this time is going upwards. And in general, in modified gravity theories, the speed of propagation of gravitational waves depends on their frequency. So if you think of the frequency during the in spiral, as you're going upwards, the frequency is going up, and you can imagine the velocity of the gravitational waves changing as a function of the time that they're emitted. So there's a frequency-dependent velocity, and on the other hand, any electromagnetic counterpart goes at the speed of light. An assumption is that photons are unaffected by modified gravity. So in all of those different models, in fact, I don't want to talk about any specific model. The only thing which I want to assume is that my modified gravity theory changes the standard dispersion relation for a massless particle. So the standard dispersion relation would be E squared equals P squared C squared. So I'm going to allow for a mass and possibly higher order terms here in the dispersion relation. So the result of that, if you think about it, is that gravitational waves have a frequency-dependent speed, which is different from the speed of light. And that has observational consequences. It means that the gravitational wave trains will travel at different velocities and as a function of the frequency of the wave, and it leads to dephasing. And this dephasing can actually be big over the large distances traveled from the source to the detector. And if you don't see any dephasing of the gravitational waves, then it gives you constraints. And the other thing that can happen in many of those modified gravity theories, which were in that picture with all the bubbles, is that there's a modified friction term, namely that gravitational waves dissipate energy differently with respect with the expansion of the universe. So in practice, what do I mean by these two effects that I want to consider? So here's our same equation, propagation equation for the gravitational waves in conformal time. In general relativity, we had this friction term alpha m equals 0. So that was a 2 cal h times h prime. And we had a propagation velocity term here, which I set equal to 1, or in other words, the speed of light. So if I want to consider these two effects, I have a modified friction term, and I have a phase velocity which differs, well, it depends on the frequency, and yeah, it depends on the frequency from the dispersion relation here. So those are the two effects which I want to consider when propagating the local solution to the observer at a large distance. So this phase velocity depends, in fact, indirectly or directly on the coefficients in the dispersion relation, and I can rewrite it in terms of the group velocity. And the group velocity turns out to be the speed of light, and I'm assuming some coefficients alpha, which are related to the A's here, and it's a frequency-dependent velocity, as I tried to draw on the figure. So what does all that do? It has three effects, observable effects. So the first one is that the amplitude of the gravitational wave no longer goes as 1 over the luminosity distance, which we studied last time, but it goes as the amplitude decays as 1 over a new distance, a gravitational wave luminosity distance, which is given by the standard luminosity distance. So on small scales, that's z over h0. And it's also, there's another term in here which depends on the modified friction term, alpha m. Then there's another observable effect, which is that the time delay between the arrival of electromagnetic waves and gravitational waves is modified because the time delay depends on the propagation speed of the waves, and they in turn depend on the frequency. So there's an extra term which comes, so that's the standard term, so that's the time delay observed at the detector, is the redshifted time delay at the source, plus an extra term, which depends on the parameter alpha j related to the speed of propagation, and of course the Hubble constant. And there's a third effect, which is precisely what I said, that there's this modified phase evolution of the gravitational waves relative to general relativity. So all of these effects, these three observable effects, for which we have data for GW 170817, they all depend on the parameters alpha j, they depend on the Hubble parameter, and they depend on the parameters alpha m. So you can try and put constraints from data. So there's certain things, constraints that you have to satisfy, right? So you have to use your observable data to put constraints on those parameters. And this graph looks complicated, and it is complicated, but let me try and make it a little bit clearer if I can. So here there are four different colors. Let's just look at the first one to start with. The first one here is a check of the method. Are we doing our analysis correctly? In other words, do we recover the right posterior on the Hubble constant if we turn off the friction modification and if we turn off the dispersion term? In other words, if we take here alpha equals m equals 0 and CT equals 1. And the answer is, thank goodness, yes. Then the second exercise you can do is to take the Hubble, to just add, the gravitational wave friction term and turn off the dispersion term, no dispersion. So the variables that you have in your problem are the Hubble constant h0 and the gravitational wave friction term alpha m, which you want to estimate. And you can see that as soon as you add alpha m, your posterior on h0, which is here, becomes very flat. And there's a reason for that, is because in fact they're correlated. You can see that alpha m here is, if you remember, this goes as 1 over h0. So alpha m and h0 in a sense degenerate. Then you can add just look at a Hubble constant and a dispersion term. This is in the case of massive gravity. And so you can start trying to put constraints on the mass of the graviton, which are down here, in blue. So constraints on the mass of the graviton. Or finally, you could do the more general case where you have all the parameters which are varying. And the long and the short of all of this, I think, is to say that the results are in good agreement with GR, so 0 mass and no modified friction term, in fact, all within 1 sigma. So at least with this one event and its counterpart, we don't see any significant deviation from GR, but this is the kind of work which continues when there are more, at least clear events with counterparts. This work can carry on. The more events you have, the tighter the constraints will be. So this was I was trying to basically give you an idea of how as soon as you modify gravity and you add friction or you add modified speeds, the constraints that you can put on those from observations. And I guess that's all I wanted to say about modified gravity.
Thank you very much. So are there questions either on the last part of the lecture or maybe on the material exposed before? No. Yes, there is one from Zakaria Belkadria.
Yes, so thank you for the great lecture. I have just a simple question. Could you comment about constraints coming from GW 170817, but concerning the cutoff of the EFT and the validity of this constraint, because a lot of theories was ruled out, but there was the paper of Claudia Jerome claiming that the energy of the cutoff allow us to say that the range of energy of LIGO is exactly the same of the cutoff of the theory. So can you just comment on this?
Yeah, so the approach that the approach taken, at least, so not the approach taken by Claudia, sorry, but the approach taken by a certain number of other people is to treat these really as purely classical theories, right? and not worry at all about their origin, right? But then your question is, right? Your question is that this constraint, I guess, on the speed of, whoops. You'll say that this constraint, or her argument is that this constraint only applies on, so what was the argument again? On the scales of LIGO,
for example,
right?
on scalar tensor theories, is it really, can we debate on it, or it's like a really constraint that we can trust it, like comparing to this argument? Because
yeah, so I wouldn't like to comment on that like that. It's something I'd have to think about, I think.
Okay.
I mean, I see where the argument comes from, but it's really quite subtle. I wouldn't like to say something.
Okay, and the second part, you assume, for example, just the modification of propagation. What about the modification of generation? And when we don't assume that the environment or the source that is valid for GR, yeah. So, for example, if in the strong field regime, we have like a theory that modify the generation of gravitational waves. So how
that's an extremely interesting question, which, I mean, I think probably there are people who are trying to work out the waveform in that case, right? And it's, as far as I know, maybe you know more than me, there's no generic prediction, is there?
I don't know, actually.
No, there isn't.
I'm just asking.
No, yeah. I know that there are certain people who are, trying to work out how screening, and if you have screening within your body, how that would affect the waveforms produced. In principle, there are other polarizations as well. The approach I took here was a simple one. It's that I know that I should my theory should reduce to GR on small scales. Okay, it's very, very simple. It reduces to GR on small scales. If I'm close to the source, then hopefully.
Okay.
I mean, but it's a very simplistic argument, and of course the calculation needs to be done, and people are doing it for more complicated theories.
Yeah, thank you very much.
So people are thanking you, Danièle.
Thank you to everyone.
I think they are also leaving, so perhaps it's time to close, unless there is an urgent question. No, but I cannot see anymore. So I suggest we stop here. Thanks again.
Thank you. Bye-bye.